All right, so power series. So this is section 10.6. Yeah. Okay. So we're gonna do power series, and then we'll do Taylor series, which is a kind of power series. So the Taylor polynomials make a comeback in a big way. All right. So we define the power series. Power series centered at x equals to c as the sum n equals 0 to infinity of a sub n times x minus c to the n. So the first thing to notice is what is that? That's what's new? Well, the a sub n isn't new, but
x minus c to the n.
Yeah, the x minus c. Well, the big thing that's new is the x, right? Oh, well, no, that's Taylor polynomial. Yeah, but this is a function of x. So it's a function, and you just like any other function, you plug in some x value, and you get some other number. But the thing is that, well, it's a funny kind of function, right? Because do you think you can plug in any x value into that?
X greater than 0.
Because it's an infinite series, right? So you have to make sure that it converges, right? Otherwise it doesn't make any sense. So, like, for example, give me an x value that it definitely converges for. Yeah, c, right? Because you plug in x equals c, and what do you get? 0. So 0 definitely converges, right? But what about x equals 1 or 2 or 3 or 4? What does it depend on? So, like, if you think about it, so let's forget about the a sub n for a minute. So let's pretend that the a wasn't really there. What would make the series converge?
Anything less when x is less than c.
Yeah, in absolute value, right? So when x minus c, this inside of the parentheses, if that is smaller than 1, then it's a convergent geometric series, right? Assuming the a isn't there, right? Okay, but then once you break out of that, right, then it would diverge. So, like, if you imagine, so that's why we say it's centered at c. So, like, let me draw a little. So let's say that this is a number line, and c is right here. So the closer the x values are to c, the better the chance it has of converging, because then you have this small number being raised to the n, right? But then the farther you go away from c, then it's going to be a bigger chance of diverging. And then, of course, you have the a sub n that also affects it, but for now we're kind of ignoring that for the moment. But I think you all agree that if this is small, the x minus c is small, that it has a better chance of converging than if it's larger, right? So power series have, and we'll define it in a minute, but they have it's called the radius of convergence. And it's basically all the x values for which it converges, and it's always centered at c, because the closer you are to c, the better chance you have of converging. So right here, this is, for example, so it'll converge, for example, hypothetically, it'll converge for all the values in between here and here, but it'll diverge if x goes outside of that range. Does that make sense? Just the idea of it. Okay. So three things can happen. Three things can happen regarding convergence. The first thing that can happen is that f of x only converges for x equals to c. So this is a pretty bad situation that says that it only converges if you plug in that number c, and so it's going to the whole thing's going to equal 0, and that's it. If you plug in any number, it doesn't matter how close it is to c, it'll blow up. And what would cause it to blow up? That a sub n, right? Which we don't know what it is, right? It could be anything, but okay. So in this case, you say that actually, just leave a little space, and we'll fill it in a minute. So I'll just put the parentheses there because we haven't defined it yet. Okay. So then the second thing that could happen is that f of x converges for all x. Okay, and we'll say what that means in a minute. And so the last thing that can happen is this: what I just told you earlier, that f of x converges for x minus c less than r, where r is some positive number. And so in this case, r is called the radius of convergence. Radius of convergence. Ooh, ran out of room. Okay, radius of convergence. Okay, so in the case 1 and 2, what we say for this first one is that r is equal to 0. So if it only converges for c, then the radius of convergence is 0. If it converges for all x, then you say that the radius of convergence is infinite. And so r is basically this distance right here, right? The distance from c to one side of the interval. So that's the r. That's where radius comes from, right? Okay, so far so good? The terminology? Okay, and then okay, so there's one thing that we haven't mentioned. Do you guys have a question? Like, what about what? Oh, yeah, that we'll get to, but something else. So here, if I look at my little picture, I'm saying that, so this tells me that it converges in the interval, right? And it diverges everywhere outside of the interval. But what have we not mentioned? The
interval itself?
Well, no, the interval, that's where we know it converges. Anything else missing or no? Don't notice anything? Close. If it's not inside and it's not outside, it's on the... No. On the edge, right? Yeah. So what about the endpoints, right? So like, what about, does it converge like right at the exact point before you jump over the edge, right? What about right there? Are you okay there, or are you not? So, okay. So the answer to that question that you did not ask, so I forced you to ask it in some way, is that you have to do extra work for the endpoints. So you don't know. It might converge, it might not converge, so you just have to test each one individually and see what happens. Okay, so now the question is, well, how do you tell whether it converges? Well, let's do that with an example. So let's say we have, we want to find the radius of convergence for, let's see, let's do x to the n over n factorial.
What happened to fun times?
Fun times with proofs? We don't have a theorem yet to do fun times proofs. It was just a definition. But don't worry, we'll bring back the fun times soon. Okay, so all right. So the question is, when does this series converge? So our question, we want to know for what x values does this series converge? Okay, so that's what we want to know. And so the usual, our usual method is going to involve a quick use of the ratio test. So if I use the ratio test, basically the series converges if the absolute value of, let's write it in general, a sub n plus 1 times x minus c to the n plus 1 over a sub n times x minus c to the n. For what values, when does this converge? If this limit, wait, I forgot the limit. If the limit as n goes to infinity of that is less than 1, right? If this is less than 1, then the series is going to converge, right? So our task then is to find the x values for which that expression converges. Does that make sense? Our strategy? So you can also use sometimes the root test, but usually the ratio test is what we're going to use. So, okay, so this is in general. So for us, so we're going to do the limit as n goes to infinity of the absolute value. So what is it going to look like? My first one. If I'm using my series here. It's going to be x to the n plus 1 over n plus 1 factorial, okay, times
X minus C to the n plus 1 over
well, what is c in this example?
0.
C is 0, right? So this is the numerator, right, basically, and then over a sub n times, so n factorial, right, over x to the n. Does that make sense? Okay, so then I simplify this a little bit, right? And I get, so the limit as n goes to infinity of, so what can I get rid of here? You can get rid of the factorial, sure. So n factorial cancels out with the n factorial that comes out of this one, right? So all I have is n plus 1 left over on the denominator. And then what happens with the x's? So x to the n and x to the n. So all I have left over is a x, right? Okay. So okay. So let's see. So this converges if what? If that is less than 1, right? So we'll emphasize here that it converges if that expression is less than 1. Okay. So for what values of x is that limit less than 1? What is that limit for all x values? It's equal to 0, right? Doesn't matter what x is. This limit is always going to equal to 0. So for what values of x is 0 less than 1? All values of x, right? So then what's the radius of convergence? Infinite radius of convergence, right? Because it doesn't matter what x is, right? Then this series is always going to converge, and that's because if you just have a number raised to the n over n factorial, the n factorial is going to dominate, right? So that series is going to converge. So this right here, this is the radius of convergence, right? Yeah.
What exactly does that mean? Radius. What is the radius?
It's the values of x for which the power series, this function, converges. Ooh, jeez. So this is a function of x, right? So this means that no matter what number you plug in for x, this is always going to converge, give you a number.
I guess what I'm kind of finding is like radius. What does the word radius have to do with anything?
Radius is what is it? Well, it's called radius because of this. Where is it again? Let me see. Okay, it's up here. It's called the radius because it's the interval centered around that number c. So whatever your radius is, that's how big your interval is. That's the distance from the center to the endpoint. So when you have you have the radius r, and you find the interval where it converges. So in this case, this particular power series, it converges for all values of x. So that's why the radius of convergence is infinite. Yeah? Kind of, sort of? It's different than what we're used to, but... Okay, let's do another one. Let's do, here's another one that's a simple one. But let me, hold on. Okay, so let's say you have the power series, 0 to infinity of x to the n. So, does that look familiar? Maybe, kind of. So, let's use the ratio test. Let's see what it tells us. So this is going to converge if the limit, as n goes to infinity, of a sub n plus 1 over a sub n, right? And x to the n plus 1. So I have so what is a sub n in this case, actually?
That's to the n over 1.
It's just the number 1, right? So all I have really is the x, right? This is just x to the n plus 1 over x to the n, right? And so this is going to converge if this ratio is less than 1, which means that basically absolute value of x has to be less than 1, right? Does that make sense? So from this, what is my power series centered at? It's centered at 0, right? So there's no x, there's no number there, so it's just centered at 0, and it converges if the absolute value of x is less than 1. So what is my radius of convergence? That's equal to 1, right? So what this is telling me is that it converges on, it's, let me draw a number line. So centered at 0, and it goes all the way from -1 to 1, right? So it's going to converge on this interval. So if you plug in a number greater than 1, then this series will diverge, right? But actually, what kind of series is that? Not a P series. It's a geometric series, right? That's a geometric, and it makes sense, right? Because geometric series, they converge if the ratio is, if r is less than 1, right? Diverge is if it's greater than or equal to 1. So this matches what we already know about geometric series, right?
But wouldn't it have to be, in that case, wouldn't it have to be less than or equal to? Or like, are we going to test for the endpoints now?
Well, yeah, normally you would test the endpoints, right? So you would test the endpoints. This one we don't have to test. Why do we not really have to test? So we would basically say, okay, well, I don't know, what happens when x equals to 1 and when x is equal to -1. And you plug them in and you figure out whether it converges. So here this is 1 to the n equals 0 to infinity. And this is -1 to the n, 0 to infinity. Both of these they both
they go straight, don't they? They just go back and forth.
well, this is just 1, right, raised to a power. So this is just 1 plus 1 plus 1 plus 1 plus 1. So this one definitely diverges. This one is 1 minus 1 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 1 minus 1. So that one also is going to diverge, right? Because it doesn't go to 0. So, but we in reality didn't really have to test them in this case because that's just from the geometric series. We already know that it diverges if the ratio is greater than or equal to 1. So we could have just said that.
I was confusing. The R doesn't necessarily have to exclude those points.
Right.
So
when you find it, you say that it definitely converges for inside of the interval. So between -1 and 1. Then to see if it converges at the endpoints, then you have to do extra testing. So in this case, they both diverge. So then what you can do is you can write down what's called the interval of convergence. And the interval of convergence is just exactly what it sounds like it is. It's the interval on which the series converges, which is in this case from -1 to 1, not including either, right? It's basically this interval that we wrote down on the number line. Right?
Is there a way to graph, like plug it into the calculator series?
Not really. Wolfram Alpha can do some of it, sometimes, a little bit. This one actually, well, we will see some of these you can write explicitly. This particular one, we actually know what this is equal to. What is that equal to, that series? 1 over 1 minus x, right? If absolute value of x is less than 1. Where does that come from? Yeah, this is the geometric series that we derived
right.
earlier, right?
That's right, yeah.
So this infinite series is actually nothing more than 1 over 1 minus x, as long as x is between negative 1 and 1. If it goes outside of that, then it diverges and it's just a mess.
So the test endpoints, they diverged, they basically did the limit of them to find that? But the
Yeah, I mean, I didn't write down much because they're really easy to see that it just diverges. Usually you do a little bit
The
more.
top one is easy to see, goes to infinity, right?
Yeah.
And then, but that -1, what does that go to? Is that just undetermined? What is that?
Well,
limit?
it doesn't exist. You can just do the divergence test, right? Because the limit of -1 to the n doesn't go to 0, so then it can't converge.
It doesn't have a limit, but it doesn't like go to infinity or either.
No, but that doesn't matter.
Okay.
Yeah,
So
it's still
like
divergence. Yeah.
undetermined
No, it's divergent, so it diverges. Okay, so I mean, so the power series, we'll do some of the applications of them, but they're very, 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 very useful in applied mathematics all over the place, because you can basically write down, it's kind of similar to, well, very much connected to Taylor series, but you know how we had the, you can have crazy functions that can be written down as very simple functions. So you can use power series to write down, you know, complicated functions in a way that makes it easier to analyze. So you'll be seeing a lot of these, you know, throughout your life as a connoisseur of learning great things. Learning great things. All right, let's do another one. Let's see. Let's step it up a notch. How about let's say f of x is series n equals 0 to infinity, -1 to the n times x to the n over 3 to the n times n plus 1. Alright, so let's see what happens. Alright, so this series converges if what? If the limit as n goes to infinity of the absolute value what's the first thing? Okay, I'll help you out. X to the n plus 1 over 3 to the n plus 1 times n plus 2. Notice I removed something. What did I remove? Yeah, why did I remove that? Yeah, we're an absolute value, right? So I can just take it out for now. So it's still part of the series, but right here we're looking for absolute convergence, right? Let's see. So times, what do we have? Times what? 3 to the n times n plus 1. Okay, but do I need to put the -1? No. Alright, so then, what can I get rid of?
So is that just
That's the n.
Yeah, so this is just the ratio test, right? So I apply the ratio test to the series to find the x values for which it converges.
You get rid of the end as well. So
Yeah.
So I can get rid of the, so let's see here.
That's the n.
So I can get rid of the 3 to the n's, and I have a 3 left over, right, on the denominator. I can get rid of the x to the n plus 1 and the x to the n. Just have an x left over on top. And then I have n plus 1 over n plus 2. Okay. And so what's the limit as n goes to infinity of that? Yeah, this is that the n plus 1 over n plus 2, that converges to the number 1, right?
Yeah.
So that's just equal to, that limit is equal to the absolute value of x over 3, right? Okay, so this has to be, for it to converge, this has to be
Less than 1.
less than 1,
So then
right?
x has to be less than 3.
Exactly.
Okay.
So this implies that x has to be in between 3 and negative 3, right? So absolute value, well, we can write maybe one more. Absolute value of x has to be less than 3. So x has to be between negative 3 and 3. So what's, oh yeah, go ahead.
Just real quick, so you just multiplied it by 3?
Mm-hmm. Yeah. Yeah, just to, yeah, so it's, you're just solving for x, basically. Right? Once you find the limit, you find the x values for which the ratio test is satisfied. So
R equals 3.
what's my radius of convergence is 3, right? So I have r equals to 3. So then what I need to do now is I need to test the endpoints. So I want to know, okay, is it convergent at x equals 3, and is it convergent at x equals to negative 3? Okay, well, let's test. Let's see. Okay, I'll do it right here so that I can do it in this little spot I created, so that I can leave everything there. So let's say x equals to, let's do positive 3. So I've got series n equals 0 to infinity of negative 1 to the n times what?
X to 3 to the n.
Times 3 to the n over 3 to the n times n plus 1. So I get rid of the 3 to the n's, right? So what do you think about that? Converges or diverges? So it's negative 1 to the n over n plus 1.
Converges to 0.
Well, converges, well, you can't say converges to 0 because you don't know what it converges to, but
It converge?
yes, why?
The bottom is going to overtake the top. That's not 1. No?
But we're talking about the series. I mean, it is true that it converges, but you have to know why.
Well, because the numerator is just oscillating, so the bottom's going to be the dominant term there.
So, I say so. What test do you apply?
Comparison test. Oh, yeah.
Yeah,
Okay,
the alternating
test, yeah.
series test, right?
Yeah.
So by the alternating series test, since 1 over n plus 1 is what? What are the conditions? It has to be both two things.
Decreasing.
Decreasing and
Let's see, the limit has to go to 0.
and 1 over n plus 1 converges to 0, right? And so both of those are obvious. If the negative 1 to the n wasn't there, would it converge?
So what was it there?
If the negative 1 to the n, the alternating part, if that wasn't there? If you just have 1 over, it wouldn't
because
converge,
be
right?
It would, yeah, it would.
It would be
Yeah.
like the harmonic series. So, okay. All right. What about at x equals to -3? So sum n equals 0 to infinity, -1 to the n times
-3 to the end.
-3 to the n over
Oh, yeah. You can already tell out the math there.
3 to the n over n plus 1. It looks very similar, right?
Mm-hmm.
But this actually,
Comes 1 to the end over n plus 1.
so what happens with the negatives?
It becomes a positive on top.
Yeah, you combine them, right? And so the -1 to the n, you get another -1 to the n. So that means that those two are going to be always positive, right? So always positive, and then 3 to the n. So all you have left over is 1 over n plus 1, and this one diverges, yeah. So it converges when x is equal to 3, but it converges for x equals to 3, diverges for x equals -3. So so what's my interval of, so the radius of convergence is 3, my interval of convergence is, so let me write it down. So interval. So did I get any new information here?
Mm-hmm.
So the interval of convergence is from -3, including 3,
No.
not including 3, all the way up to 3, including 3. So what do you guys think? Thumbs up? Yeah? What is it? Oh. Okay. So any questions?
Let's do the very
Yeah.
bottom of that again.
Very bottom of that. So then the strategy is you set up to find the values, you set up the limit, right, of the ratio test, and you solve for the limit of the ratio test being less than 1, right? Find the x values. And then once you have that gives you the radius of convergence. And so then you have your interval, right? Except for the endpoint. So then you plug in the actual endpoints themselves and individually check if it converges at the endpoints. And sometimes it does, sometimes it does not.
X and the x equals -3. How come that limit doesn't that go to 0?
Which one?
The very bottom.
This one?
Yeah.
Well, it does, but it diverges. Because, remember, just because it goes to 0 doesn't mean it converges.
Okay.
To converge, the sequence has to go to 0, but just because it goes to 0 doesn't mean that it converges. This one diverges because it's very similar to the harmonic series, right? So you can do any of the comparison tests or whatever you want, integral test, or pick your favorite. Pretty much any one of them would work. And so then you can write down your interval of convergence. Yeah? Okay, so let me give you guys one more theorem that we will not do fun times of proving, unfortunately. But we will use quite a bit. And it involves theorem. Hey. Oh, my computer's having problems. Okay, so it involves finding the derivatives and antiderivatives. Derivatives and antiderivatives of power series. Okay. So if you take a power series, so f of x equals to n equals to 0, infinity, a sub n, x, well, yeah, I'll just write it as x minus c to the n. So this is what the power series looks like, right? Let me just so that it makes it a little easier to see. Let's write out a few of the terms. So what's the first term look like? If I just start writing them out. A sub 0 plus a sub 1 x minus c plus a sub 2 x minus c squared plus, and then so on and so forth, right?
What's the A about?
A?
Yeah.
Well, that's the extra extra stuff that you have that depends on n. So like the examples we did, so like we had the n factorial, right, and then we had the 3 to the n over n, all that. So anything else that you have that depends on n, or any other constants.
For these, we don't, like, you see on the second term, we don't put it over to. Like on the Taylor series.
Oh, yeah, no. Because this is more general than the Taylor series. So Taylor series are, well, we haven't really done Taylor series. We did Taylor polynomials, yeah. So we'll do Taylor series, but those are a more specific kind of power series. So this is in general power series. Yeah. So Taylor series is a specific type of power series, which is the next section. Okay, so and then so suppose it converges for x minus c less than r. So r is the radius of convergence. So then what we can do is we can get the derivative and the antiderivative of the power series term by term. So we won't prove it, but you'll just have to believe in magic. All right, so the derivative. And let's do this. I'll leave a little space for the series written as a sum, and let's find the derivative just of this up here. So what does it look like? The first term is going to look like 0 plus
x
a sub 1, right? Plus
2 times a sub 2.
2a sub 2 x minus c to the 1, right?
Right.
Okay. Plus, what's the next one? It's not written there, but just for fun.
3 times a sub 3.
3a sub 3 x minus c squared plus dot dot dot, right? Okay, so I'm going to write this as a sum. So the sum n equals, do I start at 0? Start at 1, right? Because notice what happened to the 0th term. The 0th term,
Dropped off.
yeah, so I got the derivative. So you can start at 0, but there's no point. So let's see. So what do I have? A sub n times, what am I missing?
Is there an N before between?
Yeah, there has to be an n, right? Because notice that every term is going to get multiplied by n.
Yeah.
Okay, so it's really n. Why don't we, let's write it.
N A sub n.
So n times a sub n times x minus c to the
N minus 1.
n minus 1. Which is basically what you get if you get the derivative of this, right? If you get the derivative as a sum, you bring down the n, subtract 1, and you get exactly that, right? Okay. So, all right. So with that in mind, let's do the integral of the infinite series. So let's see. All right. Dx. What's that equal to? So what do I do with all my stuff there? We're getting the antiderivative with respect to x, right? So
Take A, the N out.
let me leave a little space here. So I don't have to really worry about the a sub n, right?
Yeah.
So the antiderivative of x minus c to the n, that's just
X minus C.
x minus c to the
N plus 1.
n plus 1 over n plus 1 a sub n, right? And where do I start? N equals to
0.
yeah, just keep it at 0, right? And I'm missing one last thing.
Dx.
Plus C.
Yeah, plus c, right?
Right, yeah.
So since I'm using a little c right here, let's use a different letter. Let's do a. So a, this is the constant of integration. So it's a plus all that stuff. And I wrote it at the beginning just because I don't want to confuse that it's inside of the series because it's outside the series. So, what do you guys think? Yeah. Good times. So one quick use of this that we don't have time for, but we'll definitely do is well, mainly when we do Taylor series, but you can have, so imagine having a function that you can't integrate, right? Don't know how to integrate, not possible. You can write it as a power series, and so by writing it as a power series, you can then integrate term by term and write it as an infinite series. So write down the integral as an infinite series and do it that way. You know, good times, everything you do. All right, questions? Well, with that, I leave. Adieu. Have a nice weekend.